Okay, thank you so much, Kate, for an introduction, and thank you everyone for joining today, for listening to my talk. The piece of work that I'm presenting today is a kind of work that we did nearly 4 or 5 years ago at IBM Research for a period of time with my colleagues, and I'm introducing them here. And we never published that work. So it's about optimizing infectious disease intervention with nonlinear cost. My colleagues, Rosalind Hickson, who is working in infectious disease area, and also work with Stefan van Kavelen, who is a software engineer, and also Olivia Smith, an optimization expert in our team, and also Manoj Gambier, who was our manager at that time, and he was actually the one that he had a lot of experience in infectious disease modeling, and he was involved in CDC to controlling Ebola. In fact, this is a nice problem that when we were introducing into infectious disease area, he mentioned his experience during controlling an outbreak. He mentioned they never had a kind of optimization tool or supported decision tool for them to decide among different interventions how they should choose which one is the best when they have limited resources or limited budget. So that's how we started to work on it. And the other thing, this is a nice group of people from different backgrounds, as you can see. And I guess that's for real world problem, multidisciplinary team is the key to start. I'm pull up this one because this is most of these talk have been presented at Informs, but I mean that's good. Your optimization background, so most of you, I guess. And Informs is a huge, big conference in optimization in US. I mean, normally 6,000 people turn up at the conference. So I presented this one at Houston 2017, and yeah, I can see the world has changed from that time that I have to explain lots of details to the audience, but this time I guess we're all experts. And also we managed to get approval from IBM to open source the code nearly late last year. But I should admit, this is one learning curve, when you want to go back to look at your code between the team of nearly, I think, 4 years ago, the code, you don't expect this to work. But when you have maths equations, it's easy. That's beautiful with maths is you can pick up your equation from 5 years ago and then 4 years ago, 5 years ago, they still are the same. Okay. So I'm going to talk about introduction to infectious disease, which I guess you all can present that bit, and explain the problem that we try to tackle in this particular problem. And for mathematical model, I present the nonlinear mathematical model that we had. And also we applied piecewise linear technique to handle the nonlinearity of the problem and some of the key findings as well. I'm just looking at the chat as well. Oh, sorry, the sound isn't. Okay, let me switch to something else. It seems people have problems with the sound. Give me a second. Do you hear better now?
Yeah, I think that's better, Hamideh. Thanks.
Thank you.
Yeah.
I should figure out what's the pattern with this Bluetooth. I think Wednesday afternoon, it's not very stable. Okay, before I start to this talk, I need to say two things. First, I'm not an expert in infectious disease modeling. So I rely on the infectious disease expert that we had. So what we did, we look at their equations that they built, and then we went from there. The second that I want to, you all know that the presentation that I'm sharing here is based on synthesized data, and it's not real data. Okay. So we tried to focus initially, used as dengue fever 4 years ago as a kind of example of infectious disease, how to control it. So did you know that half of the world's population are at risk of contracting dengue fever? And dengue was responsible for 1.14 million disability adjusted life years globally in 2013. And this is the map from WHO. This shows the number of the dengue reported between 2010 to 2016, roughly. And you can see if it's more, it's a kind of heat map. The way to read this plot is when it's more red, it shows that the dengue are reported more, and you can see here. And if it's lighter, it means less. At Australia, it's reported around 1,000 to 10,000 reported for dengue, which is pretty a lot, and it's pretty scary when I read these details. So how the dengue spread? So you might have heard by now that about SIR model, so and other models. So the dengue, let's start from one infectious mosquito. What happens when a mosquito here at the right side corner, if it's bite one person among the susceptible population, that person will be exposed 4 to 7 days, and then that person will be infectious for a period of 3 to 7 days. And what happened if any mosquito among the susceptible population in the mosquito area, if that mosquito bite an infected person, again, what happened, that mosquito will be exposed for around 7 to 15 days, and then that mosquito will be infectious for 2 to 18 days. And there we go, we are in a cycle. So the fact that now we know the story, we all learned our lesson very hard in COVID situation, we can see what's happening at the moment. The good things with COVID, there's no good things in infectious disease, I should say. There is no mosquito in COVID situation, so it's people to people. And also among the other things is in the complication with COVID is when a person is infected, normally we have, at the end, we have susceptible as SEIR model. At the end, person will be removed either by death or the immunity that the person will receive. But we don't have that story with dengue. With COVID, the person won't be immune for, and then will come back to the susceptible population. That's a bit trickier. So in real world, how they manage, how to control, they control the dengue fever, in order not to spread. Like many infectious disease controlling, there are multiple interventions, okay? And in this situation, we have, for example, they might have vaccine. Again, for dengue, they have some limitation for vaccine for a certain population. But let's imagine, let's think that all population can use vaccine. And there are two different controls that they have for the mosquito. They call it vector control and targeted larviciding. If I ever learn to pronounce that specific mosquito control. And the other intervention is isolation of infected people. So that's a kind of situation, I'm going flashback to current situation. So this is just an example. For COVID, you can, think that other intervention like vaccine, isolating infected people, lockdown, we have masks as well. So among all of those interventions, we're imagining how we can apply those interventions in a country. So this is a map of Taiwan based on, from CDC. The way to read that map is, it's a kind of heat map again. When it's more red, it means that the R naught, which I guess most of us know by now, the infectious has been, it's really spreaded really high and people are infected in that particular region. And you can see each patch has you can count it as a state or patch. In infectious disease, they call it patch here. And when it's green, it means that infection has been controlled. And the other things that you need to look at here is the population in each patch are different. Yes, so for example, here at the right side, you see we have a green, and the height of that patch is pretty high. It means people have been populated in that region. Or here we can see it's red in the middle, but the population are not very much. And bear in your mind that we have little islands here at the left side that they are pretty red, and clearly they're not very populated. So always about, fairness about how to apply those interventions in order to control an outbreak, considering those little islands with fewer people as well. So what's the problem that we want to solve here is, in terms of the population and intervention, how much should we cover from each population patch for each intervention in order to minimize the reproduction numbers with respect to the limited budget? So I use limited budget here, but doesn't mean budget. It could be limited resources as well. So this is the equation we were thinking of, okay, what is the goal? If you assume the whole population, so if you wanted to minimize the infected people, so we were thinking, okay, what is the equation for the infected, or they call it final numbers. So here we assume that the whole population is susceptible at the beginning of outbreak. So we assume that S0 is the whole population. And the total number of cases, we call it F. And this is a transcendental equation that we have, which is 1 minus of F minus S0, which is the population in the beginning, and e to the power of minus F RP, which is, this is a reproduction number, then equals 0. Mathematically, if we look at it, I was thinking, can you imagine optimizing the transcendental equation with lots of constraints as well? That's not easy. So we thought, okay, how about after negotiation with Roslyn and Manoj, and say, okay, how about if we decrease the number, R naught here, definitely if we decrease an R naught, we decrease F as well, the total number of cases as well. So instead of touching this transcendental equation in the beginning, we say, okay, we focus on R naught here. So that's a deal. Good. Now we start to look what kind of information do we have. And this is the time we started to learn lots of parameters from infectious disease area. And we try to understand the input data and also what's the decision parameters and objective and constraints. That's how I'm going to start. We assume that we know the total budget, we call it D here. We know the number of patches that we have, what kind of patches we have, and also what kind of intervention do we have in each situation, and also the cost of each intervention in patch P for one person. So we call it DIP here. And we also know the population of each patch. This is the input parameter. And the other set of parameters are specifically related to infectious parameters that we need to consider. So we have beta P, which is a transmission rate of patch P. And the other one we have gamma, which is infectious period of patch P in each patch. And the last two parameters are efficacy of each intervention. So efficacy of IP for beta is efficacy of intervention I on beta in patch P. And also we need to consider the efficacy of intervention I on gamma in patch P. And the very important parameters that we all learned right in the beginning of COVID was about R naught. And R naught in each patch P equals beta P times gamma P. So this is basic reproduction number in each patch. So now we know our input parameters. The next things is, okay, so what is a decision variable that we need to consider? This is CIP, which is the coverage. This is the population proportion coverage for the ith intervention for patch P. Definitely this is between 0 to 1. And DIP hat, this is a budget. So and then we need to decide what's the budget allocated to intervention I in patch P. I mean, mathematically, we know that the first, I mean, this would be a kind of, it is not the major in decision variable, and we can calculate it based on other decision variable. Now, one other important factor we need to consider here is, okay, after we apply intervention, we need to know, okay, how everything is changing. So we define beta hat and gamma hat P to be an effective transmission to recovery rate that makes into account the effect of interventions. So beta P hat and gamma P hat equals, I mean, each of these are equal to a multiplication of applying that intervention based on the coverage CIP that we decide to have. So let's go back a little bit, flashback to the current situation and think about, okay, can you think of the COVID situation? What does it mean here? For example, when we apply a vaccine, we decide, for example, imagine CIP in the coverage of vaccine in, let's say, Melbourne, we decide to be 50%, 0.5 of the population. So we can calculate the beta P when we apply that one in that particular region. So that is the main key for us to see how does it work? Why is it important to apply those interventions? And it causes as a reduction as well. Reduce the beta P hat here, which is, we hope that would be good. So before I start to go through the objective and constraints, I want you, while I'm explaining, think about, look, this is whatever I'm explaining here, they're all deterministic modeling. I didn't consider any stochasticity here. And definitely for real world problem, we need to apply the uncertainty here. So the aim here is we build the foundation of the model deterministic, and then in future, hopefully whoever is interested, we would like to apply the uncertainty and into the model as well. And think about where the uncertainty exists. So the objective here is we want to minimize the R0 P based on weighted by their population on that patch. This is the left side. And what is the right side? If you remember, I show you those little region with a very few population. We don't want those small population to just have an extreme, in fact, to be all infected without having any intervention. So that's why it's a kind of min-max problem. We also, UR is the upper bound of R0. We want to minimize the maximum of our RP as well. So the first equations that we need to consider, as I told you in the beginning, the previous couple of slides, we have the R0 P equals beta P times gamma P, that was the equation. The multiplication of 1 minus efficacy times the C coverage, and 1 minus efficacy of, previous one was 1 minus efficacy of beta. And the second one is 1 minus efficacy of gamma times the population. I'm sure people coming from linear background, they start to be nervous and say, whoa, we have multiplication here. Yes, stay tuned, we will fix that by our hammer of linearization. And RP hat is less or equals the upper bound of R. This is the one that, we in the objective we have here. And the other constraints we consider was RP hat should be greater than R min. Look, in infectious disease, they believe it's really good to have R, the R0 RP be less than 1. So they believe if it's less than 1, the outbreak is going to be controlled. So that's why we put it a kind of limit as well, because we didn't want one. This is maths. If we put it here, if we didn't have this equation, they say, oh, cool, I will apply all the resources that I have to this particular region because it is under control, and that would be glory. So we wanted to stop that in order to be fair and consider other regions as well. Then next is the cost-related constraints as well. So before I jump to the cost, we applied the, as I told you here, it's multiplication, and we wanted to look at this and say, okay, can we do something to minimize can we do something to linearize this equation? And from calculus from high school, we know that we know that log AB equals log A plus log B, very simple. So again, we had a deal with the infectious disease people that can I use log instead of log R naught instead of R itself. And then we use, that's beautiful, we convert into the sum, multiplication turns into summation here. But we still, if we look at this, we still have ln, so we had to, now we separate. Okay, let me remind you, in order to apply piecewise linear technique, we have first, our equations should be separate first, and second, we apply one binary variable. This is a standard piecewise linear. We apply one binary variable, gamma here, 0, 1, and we introduce another another variable which is greater than 0, omega here, and we try to any equations, we try to break it into small linear, and all of these equations make sure that they're all connected together. So now let's go to cost functions here. Why is it nonlinear? So the cost functions apparently look, in reality, may look like this. So what does it mean? The x is the proportion of the population that we want to cover between 0 to 1. And the left side, and the horizontal line, and the vertical line shows the cost associated to that. Usually when they want to apply some intervention, it could be in some, in Taiwan, they have to set up those vaccine locations. So it's a original cost. We have to consider that. And in usually the first, for example, 30% of population, in order to cover those intervention, it is more, sometimes it's more expensive. And then at some point start to be more steady. And usually the last bit of, to cover the last bit of the population, it's more expensive. They could be, they had to travel more to reach to those people, any kind of associated cost. So that's why it's not just one linear line and say this is the cost based on the population. In reality, this is different. So that's when we look at it, we say, okay, that's, again, this is piecewise linear, but on the other hand, it could be not convex. So that's why we started to think about what to do with it. And this is all I explained it. Why do we have different sections? Therefore, our cost here, which shows that each line is representing the cost and the slope of that line. Okay, so we say if we choose to cover people from that region, the cost is 0, D is 0. Otherwise, depending on where we decide how many to cover, then this is the equation we need to consider. The setup cost, SD plus that line. Again, we look at it and we say, this is not linear, but in mixed integer programming, it's a very basic technique that we can apply. We can linearize these logic constraints by introducing a binary variable alpha here, and then by putting alpha greater than equal than C, the coverage. This is a very niche and very clean application of converting logical constraints to the linear equations here. And you can try here. If alpha is 0, you will see that, okay, or if alpha is 0, what does it mean here? You can replace it here and you will get the same equations that we had up there. Okay, now we know that we had to consider apply the same techniques that we had before, the piecewise linear. Then we, as a mathematician, we always love to make everything more complex. There we go, we define psi, the similar technique, the binary variable and eta to be 0, 1, and the same techniques that we had to make sure these are all connected. Those bits and pieces are connected. So we model all of these, and also with the data that we had originally, we have it in, this is the architecture, okay? The architecture of what we built at that time. And look, when we are working with the software engineer, when that is somehow it could be very frustrating process, because they have to learn some of our optimization technique, what we're talking about, what kind of classes we're using, if it's Cplex, Gurobi, depending on the particular solver we're using, which we wanted to use a cloud-based solution at that time. And also it's frustrating for other people, you know, for example, for me to learn the code that they believe it has to be standard, which was not easy. Initially, it was really frustrated, but I believe it was paid out. This is something that I keep saying, we have to bring software engineers into the picture right in the beginning of people's project, if it's, I mean, when it's going to be a bit more serious, because imagine they need, someone else should read their code. The researcher's code is different. So the architecture that we built originally, it has DB2, it lots of things. We had to consider do cloud, decision optimization on cloud, and different modules to include our model everything. And but for later, in order, when we decided not to continue with that one, I managed to get some of the DB2 database with the other colleagues to convert them to something small like CSV. Originally, it was way out of request from our software engineers to do that, because it won't be a kind of cloud-based solution if it's just a normal CSV file. Okay, we built it. Let me share some of the interesting results with you. This is original map that we had, and after we apply the interventions that we had and choose the optimum one, this is how the map looked like. So you can see clearly that, let me, do I have, oh yeah, I have this one here. So the way to, this is the left side, the current outbreak in Taiwan region at that time, based on our synthesized data. And after we apply the intervention, clearly we can see we have more green region, but still we have some regions that are still red with the default budget that we chose. So in here, we wanted to see, okay, how does it look like, you know, how R0 will look like at the end for each patch, you know, each patch, each population, each patch R0, how did it look like when we considered different budget here. So this is the way to read this. This is the number of patch that we had, 1 to 22, and it was the more population. 22 has the most populated patch rather than the rest. And also the horizontal line was the number of patches, and vertical line shows the R0. Blue line here shows the basic R0 that we had without any intervention. That's the default that we had it here. And the way to read it, the red one is if the budget that we had, half it, how the map will look, how the R0 will look like in each patch. And the green one shows the R0 that we had, and also with the purple shows that when we double the R0. It's interesting to see where optimization choose to allocate or put more money and resources when we play with the budget, which is a kind of nice, you know, decision-making tools for the decision makers to see how much budget do they need in order to control the outbreak, and how it has chosen which patch they should allocate more budget or not. And you can see some of them didn't, you know, make big difference. And the fact that some of them are still not under 1, you see the budget that we chose, they're still not under 1. And if you remember, we had the constraints to be 0.9, stop it. And there we go. This is the original request, which we wanted to focus on the minimize the infected people, the number of infected people in that region. And this is a nice one to, after we have the results, we, when we calculate our R naught, we could then fit into our transcendental equations that we had originally I show you, and see how it looked like. Again, this is the same scenario that we had before. Here we look at the blue one represent the number of infected people, and as you can see, the same story. And then we play with the budget. If we have half the budget in red, if we had the current budget and double the budget in purple, how is it playing around the number of infected? And we can see, for example, this particular patch 19, I think. Yeah, still, it's pretty, when we apply a budget, it's observing that budget. That's how it looks like. Okay, so in summary, what we did, we apply multiple objective mixed integer programming model, and also we applied the piecewise linear to find the optimal budget allocation for each patch and each intervention in order to minimize our goal, which was weighted reproduction number. And for future, definitely we didn't consider this was the basic, this is the foundation for deterministic model. We had it. For real world, we have to consider all of those uncertainty, like those efficacy that we had, efficacy of vaccine. We all know that, at the moment they use, for example, based on the name of the vaccine, which is 0.7, 0.8, whatever. But in reality, sometimes it is between coming from a distribution sometimes. So we have to go back and consider all of those that we had. And the other things we didn't have it was, if you notice, we didn't consider the transmission rate between the patches. Our assumption was all borders are closed and no one is going anywhere, which is not true, but sometimes it was true in Australia, I guess. And the other interesting is in terms of the time horizon, we didn't consider the time horizon. For example, at the moment, we know this is the current situation with vaccine, and the research are coming out that the vaccine efficacy is decreasing. So what's the best policy that decision makers can have for future when they know that the vaccine efficacy is decreasing for the next round, and combine it with other interventions that they have. So there are lots of things we can improve and go to the next level. Okay, I think that's the end of my talk.